All right. Well, this is the piece to finish up the adaptations to aerobic and anaerobic training. We left off with this slide yesterday in class, looking at the idea that sympathetic nervous system stimulation is one of the main things that's driving how much carbohydrate usage we have. Okay, so to kind of summarize that, higher sympathetic nervous system activation leads to increased carb usage. Okay, so it makes sense because our carb usage gives us ATP faster, and so when we're under stress, we want to create energy as fast as possible to be able to move away from that stressor or avoid whatever thing might be threatening us, right? So as we train, and that's kind of shown here, as we train, sympathetic nervous system stimulation goes down at any given intensity, any given absolute intensity. So that means any given absolute intensity, we're going to be using more fat and less carbohydrates. Okay. All right. So another related but different concept is just overall total energy usage during exercise. And this is not a huge change. Okay. So these dots are very, very close to each other, right? So if anything, we get a little bit more efficient. So increase efficiency, which that means slight decrease in slight decrease in total kcals. Okay, so very, very slight, not too big of a deal, but a slight change. And this could also be from burning, moving towards fat usage, because using fat is a little bit more efficient than it is to use carbohydrates. Okay. Probably much more importantly than the other two factors so far that we've talked about, as far as some of these adaptations to aerobic training outside of the changes in VO2 max, this one here is very important. Okay, so looking at the change in lactate threshold, we have pre-trained, before training, which is the untrained state in red, and then the trained state in blue. Really what we see in this x-axis is in percentage of VO2 max. Okay, so this isn't an absolute intensity, this is a relative intensity. Okay, and so we see the lactate threshold occurring somewhere around 58% of VO2 max before training, and then after training we see that occurring somewhere around probably 78% of VO2 max. And so that's a big difference, right? So that's really going to help us to be able to sustain a higher percentage of our VO2 because we don't have a buildup in acid as early on. Okay, and we'll be talking about that one for a little bit here. So we see that big change, and that really all comes down to this. And these graphs are very important. We will come back to these on the TBL days. But so let me just explain what's going on here. This first one is rate of appearance of lactate. Okay, and the second one is rate of disappearance. I'm not sure, I don't think I know how to spell disappearance. Sorry. I should have just gone with disposal since that's what it says right there. But yeah, rate of disappearance, rate of appearance. Okay, so what we see here is pre-training and post-training values for both. So let's look at the rate of appearance first. Okay, so we see different, this is all, the x-axis is VO2, okay, and the y-axis is lactate rate of appearance. All right, so before training, at each VO2, we see a higher lactate value. All right, so really what that means is that each VO2, submaximally, we see a decrease in lactate appearance. So submax, decrease lactate appearance. Okay, but then when we get out to maximal, here, the post-training value is actually higher, right? We're going over to here versus going over to there. So that post-training value is actually higher. So maximal lactate appearance equals up. Okay, so we got that. So submaximal lactate appearance goes down, maximal lactate appearance goes up. Okay, and then what about rate of disappearance? Okay, so now we kind of have the same graph here, but kind of maybe the opposite of what you would expect. It really looks exactly the same, but all the rate of disappearance is lower after training. And you would kind of think, well, don't we get better at making lactate disappear? Well, yes, we do, but since there's not as much lactate appearing, like we saw in this graph over here, then there's not as much to make disappear, right? There's not as much to dispose of. So again, submaximal appearance goes down, but that is due to less lactate. Okay, but then maximally we see that we do get better at making lactate disappear, disposing of lactate. So that's going to be a very important factor. Okay, so the reasons for this, the reasons for the less lactate appearance, all have to do with things we've already talked about. All right, less lactate appearance because we have decreased use of glycolytic system, increased oxidative capacity. Right, and those are the two biggest ones, right? Since the body can use the oxidative system more because it's more powerful and we have more capacity with it, then we're going to use that one more, and that means we can automatically use the glycolytic system less, right? So that means there's less to appear. Okay, so but then why does disappearance being lower is during submaximal exercise is this, but maximal disappearance equals up. The reason for that is because we actually have to see a training effect with things like the lactate shuttles. Lactate shuttles increase, right? We get increased circulation, so we can circulate, we can move the lactate better. Okay, so we got increased lactate shuttles, increased circulation, increased ability of the Cori cycle. So those Cori cycle enzymes in the liver, those actually get upregulated, so we get more of those, right? So all the things that we think of that help us to deal with the lactate, all those things improve, right? So we get less lactate submaximally appearing in the blood, less lactate disappearing in the blood submaximally, but then maximally we get more. And that's helpful because and really what that means is we're, and so these two really explained why the submaximal lactate appearance was higher, but then why would the maximal appearance be higher? Okay, so maximal appearance equals higher, and that is due to the fact that we push ourselves more into the glycolytic usage. Okay, so we can deal with more acid buildup. We have more powerful glycolytic system, and so we're pushing ourselves further into that acidosis. And part of that is because we can make more of it disappear faster too, right? So all of our lactate shuttles, all that stuff is improved, so we can push ourselves further. So this is just showing that we can deal with higher levels of lactate buildup after training. Okay, so this is what I already mentioned: improvement in lactate shuttles, right? Increased removal by the liver. So all of that. Okay, and so this is all getting us to the place of looking at a change in working VO2, or maximal sustainable VO2, right? So this would be the same person, pre and post training. This would be somebody who was already highly trained, right? So their VO2 max was already very high. The VO2 max was already 71 when they started this new training program, right? So at that point, we probably don't expect to see much of more of an increase in VO2 max. But what we might see is this. We see pre-training, we see them able to sustain 75% of their max, which is 53 mLs per kg. Post-training, we see them be able to sustain 88% of that VO2 max, which is 62.5 mLs per kg. Okay, and we can see exactly what speed that translates to, right? So running speed pre of about 15.25 kilometers per hour, running speed post of about 17.5 kilometers per hour. Okay, so with no change in VO2 max, but a change in maximal sustainable VO2, we have a large increase in speed, and this is a very important factor for training, or for improving endurance performance with training, with no change in VO2 max. So again, this is all also related to epinephrine levels, right? Because the more epinephrine we're releasing, the more we're using that glycolytic system. This graph is just showing the strong relationship between epinephrine levels and lactate levels. Okay, and so the more epinephrine release we have, aka the more sympathetic nervous system activity we have, the more lactate release we have, because we're using the glycolytic system more. Okay, so it's kind of just getting back to that same point. Okay, yep, and so kind of all go with that same idea. Epinephrine release after endurance training is decreased, right, if we're talking about the same absolute intensity. Okay, so to summarize this, lactate threshold increases, right, and what that means is it takes us to, the lactate threshold occurs at a higher VO2, okay, or we could say a higher percentage of VO2 max. Okay, how does this help us? This helps us because this increases our maximal sustainable VO2, which increases our race pace. And that really is going to make us run faster, right? Okay, so that's what happens to lactate threshold. RER, submaximally. What would happen to RER submaximally? If we're shifting to burning more fat submaximally, then we're going to have a decrease in submaximal RER. Okay, so decrease in submaximal RER means increased fat usage and decreased carbohydrate usage. Okay, maximally though, if we said that the lactate rate of appearance went up, so lactate goes up at max with training, at max, okay, that would mean more, that would mean increased hydrogen ions, which that would mean increased need to buffer. Alright, so that would mean increased CO2. So our maximal RER should go up. Okay, oxygen uptake, we looked at this a little bit. There may be a slight decrease submaximally. Okay, this is that increase in efficiency, probably related to increased fat usage. Okay, we talked about this with overall kcals too, which would be very similar to looking at just oxygen uptake. Okay, so this might help us save energy. Just a little bit though, slight change, not much. Okay, but maximal oxygen uptake, obviously this one goes up. This is VO2 max. Okay, so that kind of summarizes that. Bottom line here is we get a higher race pace, right? And that's a key factor. Okay, so this is really getting back to that same bottom line. Once VO2 max is at its peak, further endurance training will not increase it. Okay, so does this mean a plateau in performance? No, right? We just talked about this. It does not mean a plateau in performance because we can still increase maximal sustainable VO2 by increasing lactate threshold, which is going to help us increase our race pace, all without an increase in VO2 max. Okay. All right, so let's look at a couple other things. Anaerobically, we've really just been talking mostly about the changes that happen to the aerobic system. What about the anaerobic systems? We don't seem to have as much ability to train our anaerobic power output, but we can see improvements of somewhere between 0 and 25% in things like wing gait performance. Okay, so some improvement for sure, some training effect. Anaerobic power improvements are probably due to really just hypertrophy, right? Hypertrophy in type 2 fibers. And then actually shifting, this would mean a shift in fiber type, giving us more fast twitch fibers, give us more anaerobic power. Okay, what about the ATP creatine phosphate system? Does this seem to be trainable? Okay, this is a study that the book talks about that looks at both creatine kinase enzyme activity and myokinase enzyme activity. Creatine kinase is one we talked about. Myokinase is also important for the creatine phosphate system. And so, can this be trained? Right. So they did two different things. They did one type of training, which is 6-second bouts of training. That was what they thought might be the best for the creatine phosphate system. But then they also did a second group who did only 30-second bouts of sprints for training. Okay, and interestingly enough, the 6-second bouts weren't enough to increase creatine kinase activity or myokinase activity, seen right here. So these blue bars did not go up, but when they did the 30 seconds of training, both those enzymes improved by about 15%. Okay, you would kind of think that the 6-second bounce would do that because that's more what we think of when we think of using the creatine phosphate system. But this study didn't show that. There have been some other studies, like it says here, that bouts as short as 5 seconds have seen some increases in these enzymes, so the verdict's kind of still out on that. Okay, but how did this actually translate to performance improvements? That's the more important part. Who cares if the enzyme numbers changed or not, if they got better or if they didn't, right? And so, interestingly enough, again, the enzyme improvements only occurred with the 30-second bouts, not with the 6-second bouts, but both groups saw the exact same performance improvements, whether they did 30 or 6-second bouts. And so this is their maximal knee extension time, going for almost a minute of doing high intensity knee extensions, looking at how long it took them for the power output to drop, and they pretty much had the exact same improvements post training, and so no changes there, no difference between the two groups there in performance, even though the enzyme improvement was different. So what this tells us is these creatine phosphate system enzymes are not the key factor in sprint performance. Okay. All right. And this is just looking at some glycolytic enzymes, right? Because we've talked a lot about some of the aerobic enzymes. What are glycolytic enzymes? So we got PFK right here, right? We got LDH. We got another one called phosphorylase, also just known as PHOS, which is very important early in the glycolytic system. Phosphofructokinase again. Sorry. I don't know why that one's there twice. And I can't seem to write, so we'll just cross that one out. We don't need it anyway since it's the second time it's there. And by looking at this table, you can kind of dissect it. But what we see with untrained, anaerobically trained, and aerobically trained, we see an increase in these enzyme levels from about 10 to 50%. In particular, in the anaerobically trained ones. Right, so we see phosphorylase right here going from 5.3 to 5.8, PFK having a nice jump there, LDH having a nice jump, and we don't see that with the aerobically trained. Okay, so the aerobically trained athletes did not improve those, and this study also looked at creatine kinase, and they saw a nice jump in creatine kinase as well as myokinase, whereas the aerobically trained did not see that. But then, as you would expect, aerobic training led to increases in the aerobic enzymes, but not the anaerobic enzymes. So there are some specific adaptations in enzymes depending on which type of activity the athletes or the subjects are doing. Okay, so what about high-intensity interval training? The definition of HIIT is that we get our heart rate up to 85 to 90% of max for the on time. For maybe that's 1 minute, maybe that's 4 minutes, something like that. And there's a couple different ways to do this: the 4x4, the 10x1, something like that. Okay. Okay, yeah, so really the bottom line in the short story here, again, this is work from Martin Gabala, the guy I was mentioning that we saw speak at the conference a couple weeks ago, and they're looking at COX enzyme activity. This is cytochrome oxidase activity, which is important for the electron transport chain. Really what we're seeing here is we see increases very similar to the same increases we would see with normal endurance training. And that's kind of the bottom line here, is that the adaptations we see with HIIT are very similar to the adaptations we would see with aerobic kind of continuous type exercise. But sometimes those adaptations are more powerful, and that's really what we're seeing here. This is a greater increase, and this is a greater decrease in time trial performance, or sorry, not really greater increase in performance, but a greater decrease in time, which is better to complete the 750 kilojoule time trial in a shorter period of time. All right, that's it.